Hello everyone, this is Puya. Today I'm just going to talk about power losses in DC-DC converters. Based on Dr. Jeff's lecture notes for ELEX 3130, in the lecture notes for ELEX 3130 we have the power losses for buck converter, and in ELEX 4420 we have the power losses for boost converters. The way I'm gonna teach them, I'm gonna just like teach them in a general format, and then I'm gonna mention like what's gonna be the difference for buck and boost converter. So for the exam questions, just remember that this is like what I expect for ELEX 3130 students to know, like how to find the power losses for buck converter, and for ELEX 4420 how to do the power losses for calculate the power losses for boost converter. Even if you've seen this part in the previous course, those of you who are in ELEX 4420, please watch the whole video. This is going to be a very good review. Also, it's a good review for the buck and boost converter concept as well. Okay, so let's just start. Before I start, I want to talk about the concept of DC, or average of a function, of a periodic function. So this part we've seen this before. So any periodic function, doesn't matter what shape it has. It can be sinusoidal, it can be square wave, something like this, as long as it repeats itself, or it can be triangular. Any periodic function, we can calculate its DC value, or also called average value. Okay, as you guys remember, this is easy to calculate. It's gonna be, so let's say like if I have a function Vt, let's say like it's a voltage, the average of that, sometimes people show it like this, sometimes people show it like this. The average of that, it's defined as 1 over the period, or you can switch this with the switching frequency or the frequency, times integral over 1 period. It doesn't matter like where the starting point and the end point are, the point is, it's just like the integral has to go over 1 period. V of t dt, right? So the most common format of writing it is like from 0 to the period, but it doesn't have to be from 0 to period. It just like it can be from any point to a plus period. Okay, so this is something I wanted to mention. You guys are all familiar with this. This is just like a review, but for the RMS value, again, this is another concept that's defined for periodic functions, root mean square value of a function. So again, if I have a function that's periodic, means like it repeats itself over time, the root mean square is defined, well, like it is like this is root. Okay, so root, this is root 2. Mean, or average, right? So like the same thing that we had for average, integral of something over the period of squared. Means like if you want to find root mean square of Vt, you just like, this is how it is defined. Okay, this is like shown as V of RMS squared. So the correct notation for it is capital V. Sometimes I make a mistake, so ignore me if I make a mistake. The correct way is like V of RMS. The same thing for Laplace transform. So like if y of t in Laplace becomes y of s, this is supposed to be capital Y. I noticed that in my previous videos I made some mistakes here, so like I used the lowercase letter, so just like I want to correct myself. Like if you have a time domain function, we usually use lowercase letters, but for S domain we use capital letters. The same thing happens in RMS. Okay, the reason this concept is very important, it's because it's basically it's very useful in calculating power. So if I have like, let's say like a waveform like this, and that's, let's say like it's periodic, right? And I want to find the power losses here. So one way of doing it is just basically find the RMS value of it, and the average power loss, it's gonna be the average of V squared over R. Okay, and this is going to be equal to, if R is constant, it's going to be V RMS squared over R. So basically it tells us like how we can calculate the power losses. So just like also something you should know is that the average of V squared is equal to V RMS squared. Okay, this is something that's how I derive this one. But just be careful that this is not equal to this one. You might have like a function that its average is 0, right? But when you just like raise it to power 2, then everything becomes positive, right? So don't make this mistake in your calculation, right? The average of a function squared is not equal to the average of a squared version of that function, right? But this is the definition of VRMS. In your notes, Dr. Jeff did some calculation for RMS value of triangular function. It's I want to do it once so that you guys like get to know like how this is done. Otherwise you might feel like confused that like where this term comes from. So we have, let's say like we have a waveform like this. This is something that we have in our DC-DC converters very often for buck and boost converter, right? Let's say this is I of something, like, okay. So this is what we have. And in this case, this is delta IL divided by 2. This is delta IL divided by 2. Okay, so if I want to find IRMS, you just basically have to do this calculation.